First, I'd like to welcome everyone here to the University of Indianapolis. For those of you who don't know me, my name is Kerry Dank. I'm the Executive Director at CEL. I am going to assume that everyone who is here because you have some sort of connection to CEL. If for some reason you found yourself here and have no idea who CEL is, if you want to get on the internet, it's cel.und.edu, and you can see all the things that we do across the educational ecosystem. One of our projects that we work on is in reading, and we are very thankful that we have a relationship that we've developed with the Department of Education, and we have some folks here from the department. And so we are appreciative of that relationship. It is helping us to expand our reach in this space. But one of the things that we sort of pride ourselves on is that we're a curious group and like to learn things and sort of understand all the nuances of the various elements of education that are perplexing and make you go, And so reading, as I'm sure you're aware, has become the hot topic of conversation in Indiana. And for a lot of us operating the space, the science of reading is not anything new. It's something that lots of folks have been doing for a long time, although it is new for other people. And so we wanted to create an event that kind of offered some access to people who maybe didn't know a lot about the research, but also provided something interesting for people who did know a lot. And so we landed on this idea of there is a lot of research going on that helps to understand how the brain works, how learning works, and social science research tends to be very different than research that takes place in a lab. And a lot of times then the work that goes on in those two spaces don't intersect like they should. And so we thought this might be an interesting opportunity to bring someone in who is working in this area and has some crossover points and maybe can help us kind of think differently about some of the work that we're doing, whether it is that you happen to know a lot about neuroscience or you happen to know a lot about reading, and try to connect the dots for us. And so we've at CEL have had the pleasure on a couple of occasions of talking to Dr. Norton from Northwestern University, who has a skill that is really valuable, I think, for this group, in that she, beyond knowing the neuroscience, she also can speak teacher, which is really exciting. And so she can kind of bridge these concepts in a way that make it pretty accessible. So with that, I'll bring Dr. Norton up, let her talk a bit about herself, and she can move into her presentation.
Thank you, Kerry, and thanks to you and your team for inviting me. When I was talking with folks from CEL earlier today, this is my happy place to be able to talk with you and share a little bit about this research. To get things started, please reach out if you have any questions. I try to do my best to get back to everybody. Here is my website, and I will post the slides for today, and we're also doing a recording, and so I'll share those with the folks at CEL. So if you miss any citation or piece of information, don't worry about getting it all the first time. We'll make sure that you hold on to it. All right, this is where I'm going to start my talk. This is a painting of the ocean in Beverly, Massachusetts, and this was the view if I craned my neck outside the window from my job where I was a dorm parent and a high school teacher for students with language-based learning disabilities. So I had 2 students at this private high school called Landmark School, and I saw each of them for an hour a day, every day, for reading instruction to high school students, and I taught 3 sections of high school biology and 3 sections of high school chemistry. So this was my first job out of college, and I quickly realized that every one of these students in my class was different. They were in a high school for students with language-based learning disabilities because the system had not given them the support that they needed. And I quickly realized that the best place for me to make a difference for kids like this was to go and continue doing research and do a PhD. And we were talking about this earlier. There are some people who are the right people to be in the room one-on-one with the people, with the kids. And there are other people who are going to talk to the adults. And that is going to be the way that they help the kids. So I went to the head of school's office. I was so nervous to say that I was going to leave and go do my PhD. So I went in there and I was trembling and I was so nervous to tell him basically that I was quitting my job. And I said, I'm going to go and I'm going to do my PhD with Marianne Wolf, whose book you got as a gift today. She's my PhD advisor. So I said to the head of school, I'm leaving to go do my PhD. And he said, okay, Miss Norton, go put us out of business. So felt very supported in that, and I went and I did my PhD in child study and human development at Tufts University in Boston, working with Mary Ann, and also collaborating with John Gabrielli and Nadine Gaub, who were two of the scientists who really started doing high-quality neuroscience studies of reading, and I'll tell you about some of the work we did together. And then after doing my postdoc in brain and cognitive sciences at MIT, I moved to Northwestern. This is not the view from my office, but it's close. I can see the lake. And this is the beautiful campus view, but my day-to-day looks a lot more like this. I have a lab full of PhD students, master's students in speech-language pathology, undergraduates, research studies, and we do MRI and EEG studies focused on early language and reading and neurodevelopment in all kinds of different ways. This is me in an EEG net. This is when we tried doing EEG outside with kiddos during COVID. We just like to do research that we hope in some way or form will benefit kids down the line. All right, getting into the nitty-gritty. I've organized the talk in a couple of different sections with kind of a big idea and some data and then some thoughts to wrap up that section. So first, kind of to Carrie's point that I think people are at different stages and understand things to different degrees, I wanted us to get all on the same page that reading disability, or RD, which I'm going to use pretty interchangeably with dyslexia, the formal definition of dyslexia, says difficulty at the level of the word. I usually say dyslexia to mean broader terms, but I also know that our state and national legislation often doesn't, and so I'm going to switch back and forth between RD and dyslexia. Difficulties with reading are complex and multifaceted, and they reflect the complex neuroanatomy of the brain underneath. So when we read, all of these many things happen automatically, and I think it's good sometimes to zoom back out and think about all of the processes that our brain is having to do as we read. So if you look from the bottom up to the top of this column, at the lowest level, we have to recognize features of letters. Things like there's a part of a lowercase a that is straight, and then there's a part that has a curve. And with that information, you can recognize that that's a lowercase a, whether it's in my favorite new font, Aptos, or whether it's in my handwriting or your handwriting or red crayon, it's still a lowercase letter a. Then we need to be able to match that grapheme or letter with its sound or sounds often that it can make in English. We need to be able to retrieve information from memory, so maybe retrieving the visual form of words that have that A in it. We need to link that with all of the processes that go into spoken language, syntax, morphology, semantics, all of those have to be working together. And then we have to put all of that together just to understand language. At the spoken language level, all of these things are influenced by executive functions like attention and processing speed. Working memory is another one that could be in that box. And phonemic awareness has its influence on these different processes as well. And then if we're asking a child to read out loud, as we often do, because it's hard to imagine what's going on in their brain, we have them articulate what they're reading, and that adds another demand as well, to actually speak the words rather than reading silently. So just a reminder of how much is going on to be able to read, so that when we talk about how complex the brain is, you can kind of think about that. So skilled reading in typical readers, like many of us, depends on the function of regions in the brain that were originally there for language and cognition. So as you'll read, or maybe have read in Proust and the Squid, Mary Ann talks a lot about how our brains evolved to read, or didn't really, because reading is invented so newly in our history as humans. We actually don't have parts of the brain that are designed for reading. We have to take parts of the brain that were designed for language and for cognition and for visual recognition and kind of link them up to make a reading brain. So these are some of the regions that are really important for reading. So what we're looking at here is the left hemisphere. Here's the front of the brain. The eyes would be up here. Your ear would be over here. This is the back of the brain and the top of the head. And so we've got regions up in the inferior frontal gyrus, the temporal parietal junction, the superior temporal lobe, and in the fusiform gyrus and inferior occipital area. So these are the main regions when we're reading that are doing the most work. I want to point out that the whole brain looks kind of gray and like it doesn't matter, but that whole myth of you only use 10% of your brain is total nonsense. Our brain is such precious real estate that we use every little bit of it for everything we can. This is just what we use more for reading than for other activities. If we look then at not just which areas are involved, but what are the connections between them, these are 3 of the sort of white matter tracts or highways in the brain that are really important for reading. So these are essentially white matter bundles. If you think back to your high school biology, remember myelin, those little nodes that make information travel fast. So these are bundles of axons. And if you look at where those happen, and I do my kind of fun PowerPoint magic and slide these over, you can see that the regions that are important for reading are also connected by these sort of highways, so that information can travel between them really quickly. So reading depends on not just these different areas being able to work well, but having strong connections between them. So when I was in college, I got interested in the brain and in reading, and this was around this vintage. And the first few MRI studies that looked at people with dyslexia, often adults, often very small groups, like 4, started to find a pattern of results. And so this review paper chose to use shapes to stick, it's almost like sticking little stickers on the brain. And they said, look, everywhere is, we're looking all over the brain, but what we're finding is that these groups with dyslexia or reading difficulty are showing less activity in that region I showed you that was yellow a minute ago, this region, the left temporal parietal junction. And we know that this region is important for phonological processing and for letter sound integration. So, done. 2002, we have solved dyslexia. We have figured this all out. I was in college. I did an undergrad MRI study. I did an undergrad thesis on MRI, which is ridiculous, about spelling, because I was like, oh, well, spelling will be different. We'll figure this out, and again, we'll be done. I'll move on to something else. It's not even close to this simple, is what we have realized. So this is a much more recent paper, and this is plotting the point at which there was the biggest difference between a dyslexic and a typical reading group in tasks in the MRI scanner where we asked people to do tasks that involved either phonology or orthography. And if you look compared to that last brain, you see the confetti here compared to like a couple of little stickers in one spot. And what this tells us is that there's a lot of variety across studies. Studies are finding differences between typical readers and struggling readers essentially all over the brain. And so why is this the case? Is it true that everything in the brain is different, or is something else going on? One reason for this, I think, is that we have moved in our evolution of the way we evolve in the science of reading and understanding of reading to thinking about sort of a single deficit causal model of dyslexia. So the revolution of sort of the idea that phonemic awareness is the single core deficit in dyslexia, and we just measure that, and that's all we need to do. We can screen for it, we can assess kids, and we can know if they're going to have reading difficulties. And I think we have moved past this in part from work from Marianne and others, pushing us to a multi-componential view of dyslexia, where it's not just a light switch and it's present or absent with one kind of dimension, but more like a soundboard like this, where there are all of these different dimensions, and it's not just off or on, there are gradations and variety, and lots of different ways that things can happen. And there are not just risk or vulnerability factors, but also protective factors. We were talking earlier today that you might have a child whose brain is set up in a way that might make reading more hard, but if they love stories and have caregivers who can support them and read to them a lot, and they have great working memory and all of these different things, those can be protective, and they might not have as much struggle with reading as someone who on paper looks very similar. So why this shift from first we thought the brain was just, we've got this one little spot, to now all of the kind of confetti through the brain? Does anyone want to be brave and guess or suggest a reason why we might have kind of seen this shift over the last 20 years? Yes?
Better technology.
Better technology. Say a little bit more.
Well, the fMRI technologies have developed to the point where we can see more.
Yes.
We have better capabilities
Totally. So fMRI technology has come a long way. We have better resolution. We can get things, we can see things better. Any other ideas? You're teachers. You must embrace some of the awkward pause, right? How about one more person give a guess that could complement that? Use of technology. Oh. Yeah, our culture is different, the way that we engage with media and reading and things like that. Is that what you're thinking? Awesome. Okay. Great ideas. So I'll offer a couple of ideas that I had that might explain this and talk about what I think it is. So is it that reading or dyslexia itself is getting more complex? Probably not. We haven't had so much change over the last 20 years or so with media that could do it, although that may play a role. Is our brain imaging technology getting better? To your point, yes, definitely. And I'll talk a little bit about why you shouldn't probably trust any MRI studies that are more than 20 years old. And or are scientists getting more kind of crotchety? I spent a long time trying to figure out what the right word there was. That's really the one that worked for me. I think what we've come to understand, more so than just that there's a single phonological core deficit in dyslexia, is that there is such a complex sort of ecosystem of things going on. And I really like this slide from my colleague Fumiko Haft and her group showing kind of all of the cognitive and socio-emotional potential protective factors that could take the underlying biology and alter a child's outcome over time. Another thing to the point about MRI technology that I learned and that I really is central to our work is these are 4 brains of kindergartners that I put in an MRI scanner. We can use this awesome software that goes through and looks at the anatomy of their brain and can actually label the different parts of the brain for us. So it saves us a lot of time. And it makes these beautiful color-coded maps. So if I say, look, here are 4 kindergartners, do you notice anything about similarities or differences between their brains? Do they look more similar or more different to you? Everybody's got all the colors, you got all the pieces, but for example, if I highlight this region here, the temporoparietal junction that we've been talking about, if you look at the differences in shape and size and location, so like this kiddo down here, this reaches basically all the way out to the back of their brain. This kid, it comes a little bit more forward. They've got this cool little like omega sign in there. It's really fun when you're a neuroscientist to look for what your brain, kind of fun shapes are. I have a friend whose brain, sulci and gyri literally spell USA in one part. It's like, I think you should get like a presidential citation for that or something. But at first look, brains are really similar, but brains are actually hugely different just in typical variation. If I got to scan all of our brains in the room today, we would show all of these different, just subtle variations that are just the nature of how complex developing a brain is. So there's so much variation across people that when we try to group everybody together and compare a group of typical readers to a group of struggling readers, we're losing all of this nuance, which makes it really hard to see true differences that are there. And so our modern technology is much better at dealing with this. We also have some methodological challenges in understanding the brain basis of reading. So who's ever had an MRI? I've had boatloads, so lots of people. So it's not a place you probably did a lot of reading. Unless you were in a study, right? It's noisy, it's dark, it's confined, and it really only works if you stay super still. So we can put words up on a screen and have people read them, but this isn't the kind of reading that we do in our everyday lives. It's not the environment where we learn to read. And so we can learn a lot of things from MRI, but not everything. So we do things in our lab now that look a lot more like this. So we're doing more EEG because even though it doesn't tell us about the structure of the brain, it tells us about the functioning in time really precisely. And you can do things like let people actually sit and read a physical book, or you could even let autistic toddlers and their moms hang out and interact and look at their behavior and actually look at how similar their brains are, which are some of the things we're doing in the lab. So old MRI methods were really bad at dealing with motion artifacts. So if you move more than, so imagine a millimeter, right? It's really small. If you move more than 2 millimeters during the 5-minute MRI scan that I give you, it looks much more like this than like this. And if our goal is to be able to kind of go and draw these lines between gray and white matter, we can do it really easily on that side. We can't really do it at all on this side. It kind of looks like the oatmeal of a brain. So we have to be really careful about that, and our old MRI methods were not good at catching this and dealing with it. We've come a long way in that, but still important. We also have to rely on averaging groups together, like I mentioned, so now we're better at kind of accounting for variation across people rather than assuming all brains are the same. And then the last part that is really different, and the reason why I would tell you if you're ever looking at an MRI study from before, I'm going to say 2010, we were really bad at statistics then. So imagine I gave you this jar of marbles and I said, close your eyes and reach your arm in and try and pull out a black marble. The first chance is pretty low that you're going to pull out a black marble. You can see there's maybe a couple in there. But if I gave you 20,000 chances, you would pick out a black marble for sure, many times. And that's what happens when we do MRI. We divide the brain into 20,000 little quadrants, essentially, and then we test if each quadrant is different between groups or different in its activation. And when you test something that many times, you are for sure statistically going to find something that is different. It's just the way we do our statistics. We assume that something has to be unusual to be significant. And so when we test many, many, many times, like old MRI studies did, they found lots of things that weren't there. So be very skeptical of any old MRI studies. So to wrap up this section, as we do studies and as you read studies, we need to think rigorously about the differences between people, how much we vary, and think about these statistical comparisons to be able to find valid conclusions. And then remember, the other thing I'd like you to take away from this is that the brain basis of dyslexia, reading difficulty, is as complex as the variation we see across kids. So for every kid that you see who's a little bit different, their brain is a little bit different. And so we have to keep that variation in mind when we're drawing these group level conclusions. The next thing I want to talk about is that the characteristics of reading difficulties exist in the brain before kids learn to read. So we did a meta-analysis a number of years ago, a study of studies, where we looked at studies that looked at pre-readers. So before kids had even learned to read, what was different in the brain? Scanning 5-year-olds is a boatload of fun, I can tell you. But enough studies had done this so that we could look across those studies. And this gives us some big advantages because it gets rid of the quirks of one little study, depending on, if your kids all went to a certain school or lived in a certain area or from a certain demographic background. By studying across studies, it lets us make more strong conclusions. So we found two main areas where the brain was already different before kids even started learning to read, when they went on to later have reading problems. And these are two regions you might start to realize they're going to be a bit of a theme through everything. So one is the fusiform gyrus, which is also called the visual word form area. And that's the spot down here in blue. It's kind of underneath the bottom of your left temporal lobe. And it is an area that's really neat because it becomes more active for word reading than anything else once you learn to read. So we've done some research to show that before kids learn to read, this area is actually equally active if you look at faces or words or scrambled letters or things like that. But it's already connected differently to the rest of the brain before kids learn to read, and that's going to constrain how they learn to read. And then the other region is our old friend, the left temporal parietal junction. Again, already different before kids learn to read. This is one of the studies we've done that went into this meta-analysis that looked at phonemic awareness. So we knew that phonemic awareness was going to be an important predictor of kids learning to read. And so we put these 5-year-olds in the scanner, and they couldn't read yet, and we gave them the CTOP blending words measure. Who's ever given CTOP blending words? So if I say the easy items, or like if I say, what word do these make? Cow, boy. Good. And if I say, what word do these sounds make? T. Good. great, you pass your phonemic awareness test. But essentially, a higher score on the right on blending words is better early phonemic awareness. And then on the y-axis, we're plotting a tract, a connector from the front inferior frontal gyrus to the temporal parietal junction and down into the occipital lobe. And we're plotting a measure called FA, which is fractional anisotropy, and it's a measure of how well organized the tract is. So essentially, do you have lots of white matter axons that are all bundled up and going in the same direction, or are they all kind of like tangled and crossed and not very efficient? So you can see we had a really strong correlation here that as you had a better blending word score, even before you learned to read, you already had a stronger organization in this tract. And one of the cool things that we did in this paper is we actually did the visualizations of different kids' arcuate fasciculi. So the 4 kids in red dots here with scores of 0, 3, 9, and 11 on this measure, you can see as we go from left to right that we start out pretty small in size, so they get bigger and bigger and bigger, so we have an increase in volume. You also have more and more warm colors, which means better organization. So even before kids learn to read, this part of the brain that's going to kind of link up all of those reading areas is smaller and less well organized in kids that were weaker in phonemic awareness, and it didn't matter how old the kids were or what their home literacy environment was. Those things didn't explain these differences. Then my colleague Nadine Gaub and her lab scanned babies, which now we do this all the time, but it was super rare back in 2015 to try to scan sleeping infants. And so they looked at babies who had a family history of dyslexia, because we can't, despite best efforts, get 1-year-olds to do the blending words task. But what they did is they looked at this same tract and they compared kids with a family history of dyslexia, because we know there's about a 50% chance that if you have an adult and a biological parent or a sibling with dyslexia, that child will have dyslexia. And we're comparing the kids with family history of dyslexia in blue to kids without family history in yellow. We're again plotting FA on the y-axis, so more is better. And here we're looking across the tract, so going from the front down around its little elbow there. And all along the tract, you can see that there's no overlap between the yellow and the blue lines. So through the whole tract, these infants who had a family history of dyslexia were showing the same pattern of weaker organization of this tract that's going to be really important to support our reading network. So I just told you how great we can identify these things before kids can read. And so one of the questions I get asked most often is, so can I bring kids into your lab, or where can I send my child to go and get an MRI to tell us if they have or will have dyslexia? So should we go get kids an MRI? Both Taylor Swift and I say no. What I didn't really talk about here is that we're looking at group averages, and even when we see these correlations, the scatter plot that I showed you here, we're not perfect. We are not at the level that we can make a determination about an individual kid. Like if we looked at this kid down here, we would say, wow, their FA is really low. We might guess that they have really poor phonemic awareness, but they're actually kind of in the middle of the distribution here. So this is back to the problem of everyone is so different. Any one brain measure is not enough to tell us whether they're going to have reading problems or not. So we're much better sticking to our behavioral measures and our intuition and our understanding of what this given child can do than MRI for now. Despite what I probably would have told you in grad school, I really thought we would have had all of this fixed, and we would just take out one of the custodial closets in each school and stick in a little $3 million MRI scanner, and we'd save money in the long term. I think we can all agree, $3 million for the next, thousands of kids to go through and be able to be identified early, I think is a great investment. But we're not there yet. I think we're very far, actually, from being able to use a brain scan for diagnosis. All right. I'm going to take a little chunk to focus on my favorite, the component of reading I would take to a desert island, which is rapid automatized naming. So rapid automatized naming, or RAN, is a predictor and a correlate of reading ability. And so Marianne Wolf and her colleagues have done a lot to take this work to studying kids. It was originally identified as a way to study post-stroke patients who seemed to be accurate in naming things that they knew, but they were very slow. And so the definition of RAN is the ability to efficiently name aloud an array of repeated familiar items, such as objects, colors, letters, or digits. I want to highlight a couple of parts of this. I'm going to walk and talk. So efficiently first. So this efficiency means accuracy and speed. So because we're looking at automaticity, we only want to do a RAN task for items that someone knows. So if a child doesn't know their letters yet, and you give them an array of letters to name, it's not a RAN task because they're not yet automatic. We're going to have them name aloud because we want to hear what they're doing. We could have them name silently, but we're not able to kind of track and get all of the information. So we're going to have them name aloud. Importantly, what differentiates a RAN task from a lot of other tasks is that we're asking them to name an array, a grid of items. In the same way that when we read, we have to go left to right, top to bottom, and do things kind of over and over and over and kind of keep our brain engaged, a RAN task is going to do the same thing. We're going to use repeated items because the goal here is not to see if they know the items. Remember, we want them to already be accurate. We want to know about their automaticity. So we're just going to give them the same items over and over to make it as easy as possible so we can focus on automaticity. And as I mentioned, they need to be familiar items because the goal here is not to assess accuracy. We can use objects, colors, letters, or digits. Once kids know their letters or digits, that is a better predictor and indicator of their later reading because it's more similar to reading itself. And the reason we think RAN is such a good predictor, which I'll talk about, is because it shares so many processes with reading. It's kind of a microcosm of reading. It does so many of the same things, just in a simplified form. So we are going to do a quick RAN exercise. Get your naming pants on. So what we're going to do is, just like you were a child who is completing this task, I'm going to tell you that what I'd like you to do is start at the top left and name each of the items as fast and accurately as you can. When you finish the first row, go on to the second row and keep going until you reach the end, going as fast and accurately as you can. And you are all going to do this aloud. And what I would like you to notice is how much variation there is in what time. You will hear kind of the cacophony of everyone naming, and then you'll hear it sort of start to trickle off. You are not all going to finish at the same time, and that tells us something. All right, are you ready? Now, don't do the thing where I say go and you don't start naming out loud. Name aloud. On your mark, get set, go. What did you notice? P's and D's are confusing sometimes, and you might notice, say, why did you put P's and D's in there? Because we know too that kids can sometimes make reversals. It's not a hallmark of dyslexia, but we want them to have that automaticity for P's and D's, so it is very purposeful that there are P's and D's in there, and some versions of this don't have reversible letters. I think this was a well-designed one. Marianne designed this one. This is from the RAN-RAS tests. Anything else that you noticed? Did you feel like you were pretty consistent in your timing as you named across? Did it get sort of slower and tougher as you went? I should have brought the audio, but I have some great audio of kids doing this task, and I have seen literally thousands of kids do this task, and some are like metronomes. They're just like D-S-A-P-O-S-P-D. They're just super fast and consistent, and then you see other kids who start fast, and around here, it starts getting really messy. And they're like, S, D, They know the letters. They've already said each letter like 3 or 4 times, but they really start struggling. And it's fascinating to see this really unfold. But the amount of time it takes you total to name in a grid like this, we're going to compare to your peers of the same age. And this is correlated with your current reading ability. And if we do this in kindergarten, it's a really good predictor of your later reading ability. So as I mentioned, this is a microcosm of the processes involved in reading and both a correlate and a predictor of reading ability. This has some synonyms. It gets called different things, which I want to point out. It sometimes gets called rapid serial naming or naming speed or rapid automatic rather than automatized naming, but it's not the same as discrete naming. It's also not quite the same thing as letter naming fluency. I didn't go too far into that here, but the focus is really here on knowing, like, accuracy already being set and focusing just on efficiency and kind of taking out the demands of all of the different like case sizes and fonts and things like that to really focus on automaticity. But it does share some characteristics with letter naming fluency. So my lab did a meta-analysis. Again, meta-analyses are great. You don't have to collect any new data, but you can draw really strong conclusions. So a meta-analysis, again, is a study of studies. So we looked at all of the other studies out there in the world that had given a RAND measure in kindergarten and then assessed the same kids' reading in 2nd grade or later. And this is great because it can both tell us how strong that relationship is, but also let us assess things that may sort of change the strength of that relationship. So for example, we could look at whether the RAN reading relationship is stronger when we use alphanumeric stimuli, like letters or digits, versus objects and colors. So for example, we might pull this first study out of the literature, and they had 55 kids that are 6 to 10 years old, and they gave them a RAN letters task, and then they gave them a speeded reading task, like the tower. And then another study might have found that the relationship was not quite as strong, and they had a little bit smaller of a sample. The kids were a little bit older. They also used a RAN letters task, and then they measured their reading with a non-word reading task. And so we don't know whether the RAN reading relationship is strong or moderate, and we don't know which of these factors it's due to. So meta-analysis lets us answer these questions. There were some existing meta-analyses of concurrent, so meaning on the same day, essentially, we bring a kid in and we give them a RAN measure and a reading measure and see what the correlation is. So these are correlation coefficients, R's, so they range from 0 to 1. And if we look at these 2 studies, which both, when you look at their sample sizes, pretty good. I'd be pretty psyched if I could bring 26,491 kids into my lab. But that's the beauty of meta-analysis. You don't have to. So the correlation between RAN and single word reading accuracy in these studies was 0.46 and 0.45. This is across all ages and languages. And the correlations with passage comprehension were pretty similar here, a little bit weaker over here. And then if we look at any accuracy measure versus any speed measure, you can see that there is really consistent correlations between accuracy and RAN, and a stronger relation when we look at speed, which makes sense because the more similar 2 tasks are, the more likely they are to be related. There is one small study. This is my favorite study. This is the study I would take to a desert island. It looked at all of these different predictors of kindergarten reading to later different reading abilities at different time points in kindergarten. So if you're curious, let me know and I'll send it to you. It's not a big study, but it's just so cool. So they looked at RAN to 2nd grade reading in just this small sample now, 189. I used to never call that small. They found a really similar value. Remember, we're 0.45 and 0.46. Similar to passage comprehension, and again, almost exactly the same 0.55 correlation. So cool. And now we are going to do this study in my lab. Indianapolis, Indiana's own Sean McQueenie, who is in my lab, PhD student. He's now a postdoc at McMaster University in Canada. Very proud Indianan. I learned a lot about Indiana from him. And another PhD student, Jenny Choi, did this work. And so they looked at all of these studies that predicted later RAN in the same kids. So now our sample size is 10,513. It's pretty awesome. So overall, the correlation between earlier RAN back in kindergarten and your reading 2+ years later was 0.4. So almost as strong as if we measured it on the same day. Then they did all of these neat comparisons. So they compared if the correlation was different, if we looked at accuracy versus efficiency. No, it was pretty much the same, interestingly. If we looked at timed versus untimed reading measures, pretty much the same, interestingly. And reading comprehension measures versus any other type of reading measures, they're actually pretty the same. Can anybody guess why we didn't see a stronger correlation like that 0.55 that they saw with the other speeded reading measures? It took us a while to figure this out. In second grade, are kids super fluent and accurate? Super fluent and efficient? No, they're still at kind of the accuracy building stage. So accuracy and speed are pretty highly correlated in second grade. They're not kind of moving past that stage where they're really, really fluent and speedy yet. But we did see a difference in a higher correlation with real word reading than non-word reading, which makes sense. So that made us think, well, there's kind of the phonological component to non-word decoding that's not there in real word and sight word reading. So what we did is looked at whether phonemic awareness was sort of a moderator of this relationship. So what if we also controlled for phonemic awareness, because lots of studies did that, and even once we control for phonemic awareness, there's still a significant association between kindergarten RAN and later reading ability. So this tells us that all of our schools should be using RAN in their screening battery. Like it takes 1 minute to administer. There are tons of normed versions. If you don't have a normed version, you can create one that you can use in your school. But this is the fastest, basically easiest measure you could give to try to get an idea of kids' later reading, especially their reading speed and fluency from kindergarten. And we can talk more about this. I have a review paper about this. It's something that I think is one of the easiest changes we can make. Okay. We're going to talk about RAN and the brain. So behavior is good, but we can also sort of understand why this relationship is there. So if we can look at the brain regions that are involved in RAN, we can see what are the different processes that are going into it. And if RAN is truly a microcosm of reading, like I'm trying to convince you, we should see a lot of overlap. So a study, not mine, looked at RAN and reading in college students, but no reason it should be different in kids. So here's what they found. Now we're looking at slices of the brain like kind of chopped off like this. So we're looking down on the top of the head. The eyes are up here, and the ears would be on either side, and this is the back of the head. And then this is up tall and going all the way down through the brain. We've got RAN letters over here and RAN digits over here. What do you notice about the similarities or differences between RAN letters and RAN digits? More similar or more different? Some differences, some similarities, right? You can kind of say both. What do you notice about how much of the brain is involved? Is it a lot of brain or a little bit of brain? It's a relative lot of brain. We got stuff back here in the temporal and the occipital lobes. We got stuff up in the frontal and motor cortices. So relative similarities between the two. And now we're going to compare this to the same people in the same scanner doing a rapid word reading task. It looks really similar. So all of these parts of the brain back here that are activated, that you've got, some activity up here, all the way up here in the middle, there's substantial overlap between the parts of your brain that are active when you are doing a RAN task and when you're doing reading. So we can take this to the idea of the double deficit hypothesis. Who's ever heard of the double deficit hypothesis? Oh, you're acting like you're shy back there. Like, I don't know if I've heard of it. So the double deficit hypothesis, which was put forward by Marianne Wolf, our buddy whose book you have and my mentor, was back in 1999, she and her colleague Pat Bowers said, look, we know that there's a phonemic awareness deficit that causes reading problems for many kids, but we also see these kids that have really good phonemic awareness and they're still struggling to learn to read. So maybe there's like a multifactorial cause or view of reading that we should be adopting. But they thought that if they were like, look, there are many deficits that could cause reading problems, people would freak out and not believe them. And so they said, all right, how about this? We're going to say there might be 2 different deficits that could cause reading problems. Deficits in the processes that support RAN. So it's not just RAN itself, but it's kind of these parts of the brain being able to connect well and efficiently that would make you good at RAN versus phonemic awareness. And if you have both of those deficits, those kids are going to be the poorest readers. So this has been shown now behaviorally in so many samples in so many languages. It's very well validated, and this was just that first step toward a multi-componential view. So we did a study to see if their brains were actually different, because if their brains looked exactly the same, it wouldn't make sense that they had different underlying deficits. So here we had 90 kids, and we grouped them into good readers, essentially control with no deficits in RAN or PA, or deficits in PA, or RAN, or both. And we looked at their brains. Well, they did a task where they read words and decided if they rhymed. And here's what we found. Totally separate regions in the brain that were more active for kids who had phonological difficulties versus RAN difficulties. So you might, again, see our old friends, our BFFs, left inferior frontal gyrus and left temporal gyrus here in the kids associated with phonological ability. And we saw this kind of gradient such that the control readers used these regions the most, the single phonological deficit readers used them a little bit less, and the kids with both deficits actually deactivated these regions compared to when they were resting. And then the kids with RAN difficulties had a difference in the right cerebellum, which is really involved in timing and coordination and articulation, not surprisingly. So we know that there are these differences in brain activation and connectivity as well, which I didn't show you, in kids with PA and RAN and double deficit subtypes. And so this tells us that there are different subtypes, but they're also real in the brain. And so that's an important, I think, kind of takeaway thing, that we see these differences and we can say there are subtypes or different deficits caused in dyslexia, or deficits that are causal to dyslexia, and they really are different in kids' brains. Okay, just checking the time. We're good. Another totally different way of doing this, I talked a lot about MRI today. I mentioned we're doing more and more EEG. EEG is great because it is really good about telling us timing information, whereas MRI isn't. And it is cheaper when you're starting out as an assistant professor. It's also portable. We can take it to schools. And you can actually see people's faces while they're doing it. So it's kind of much more fun. So there's a way of looking at EEG in the brain with this task called the mismatch negativity. And this is telling us about how fast our brains are processing sound changes. So essentially, how automatic is our brain at processing sound? And this measure, which I'll tell you more about in a sec, in previous studies in kindergarten was a better predictor of kids' 5th grade reading than any behavioral measure. RAN came in second. And really neat, we can do this on babies. And actually in Finland, they get babies basically after delivery, they wipe them off and stick an EEG cap on their heads because they want to look at kids before they've had any language exposure out of the womb. And they see that 4 hours after birth, this signal is already different in kids with a family history of dyslexia. So I kind of have a dream to live in Finland and be able to do this research someday. So this is what this task sounds like. So we would just have you come into the lab and sit and listen to this for 20 minutes. Could you hear it? I'll play it one more time. What did you notice? There was a da. So you get a da about 10% of the time in that stream of ba's. You can imagine how exciting that is to listen to for 20 minutes straight. That was 3 seconds. So what we do is we look at your brain waves as they're going by, and every time we play a sound, we sort of put a little marker in. Oop, that one jumped out of order. And we look at that segment of brain waves to see what your brain was doing. And this is just little sensors all over the scalp that are picking up the electrical activity in our brains. And when we lump all of those times together that you heard the standard sound, so that's the ba, that's in blue here. And what we're plotting is the change in electricity on average every time you heard that ba. And so time since the ba started is on the x-axis. So this happens really fast. This is a half a second that I'm showing you in this 7-foot wide figure here. And then electrical change, and we do a weird thing for very old-fashioned reasons, and we put negative on the top. Don't worry, that's just how it is. So what happens is, before the sound starts, Importantly, the ba, which is the standard in blue, and the da, or the deviant in black, look very similar. This is good because it tells us that our children did not have like extrasensory perception and they did not know what sound was coming next. If they were different before they heard the sound, we would have like children with special powers and we'd have to send them to Hogwarts. So that didn't happen, that's good. And even once the sound starts, for about the first 100 milliseconds or 1/10 of a second, these waves look the same. And that's good because in a 1/10 of a second, you can't yet tell whether the sounds are different. But around 100 milliseconds, they start getting different. And what you can see in red here is just the subtraction, the difference between the two. And so early on, we get a little bit of a difference, and then later on, we get an even bigger difference. And what this is that early on, our brain is like, oh, that was a different sound. And then just a moment later, and that happens in our auditory cortex on both sides of the brain, and then that information goes up to our frontal cortex. And our frontal cortex was like, cool, that different sound was a da. So you get kind of this like recognition of something being different, and then conscious realization of what it is. And the cool thing about the MMN is that this part, the like subconscious stuff, you can get this in babies while they're sleeping, which is very convenient. You can get it in people who are in a coma, and the degree to which this is there actually predicts if they're going to wake up from their coma. It's like how intact your brain is for processing. And this is also very similar to the signal that we use in newborn hearing screening. So if you've ever seen a baby get their newborn hearing screen, they play some clicks and they measure their brainstem, but it's the same idea that you get this sort of, without having to pay any attention, automatic processing of sound. But then the cool part is, especially this later part often relates to kids reading. So we had a group of kids in kindergarten, and we broke them up into whether they had low RAN or typical RAN, and low PA and high PA, or typical PA. And so you can see these are the difference waves. So you get this kind of difference at the 100 to 200, and then a bigger difference from 300 to 500. And we're just plotting different parts on the scalp up here. So this is kind of hard to make sense of, even for me, and I made this figure. So let's look at it a different way. Now I'm showing you the electricity on like a map of their scalp. So their noses are up at the top, their ears are on the side. And blue means more negative, red means more positive. And so when we look at the low RAN versus the typical RAN kids, if you just kind of glance, you compare these two. This is the early, this is the late. You can see like the shape of this blue area is kind of different. And so what we actually measured was the amplitude, but also the laterality, how left or right lateralized this signal was. And for the low versus typical RAN kids, the RAN was significantly more right lateralized, which is actually what it's supposed to be. Weirdly, you would think language left lateralized, but it's not in this case. This was significantly different in the laterality index for both of these, the early and the late. So sort of how much signal strength is on the left versus right. So then if we switch and look at good versus poor PA, now here are the maps. Oh, I drew you a helpful circle on this one. The amplitude, just how much blue there was, only in the late was different. And you can see this a little bit more clearly, that you've got kind of more dark blue over here than you do over here. So the neat thing about this is that the different signals about this very easy listening task, very simple listening task, it's not like we're playing elevator music, correlated to different parts of RAN versus PA. So this task where you're just hearing that ba, 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 da, ba, tells us about both your sort of sound processing intactness, but also the automaticity of your system. And that's why it relates to both RAN and phonological awareness. And one of the things I'm really excited about that I don't get to talk about today very much is Northwestern is one of 27 sites around the country that's starting a new study funded by NIH, where we are going to follow 7,500 kids across the country, starting before they're born. So we're recruiting pregnant parents in the second trimester and following the kids until they're 10. And we're getting this task in all of them. I'm so excited. And we're going to get their MRIs and their reading ability and and everything about their families and just like everything you could ever want to measure. It's called the Healthy Brain and Child Development Study if you want to learn more about it. But I was really pleased that I kind of convinced them to put this in the battery. Okay, take-home messages for this section about RAN and PA. I didn't write them up. I thought maybe I would challenge you to see if you could summarize what the take-home messages about RAN are. Does anybody want to be brave and suggest something that you kind of took away from this section focusing on RAN? Yeah.
RAN activates similar parts of the brain.
RAN. Yep.
But I actually have a question
Okay.
about that. You talked about the outcomes were single word reading accuracy.
Yeah.
And then comprehension. Are there many studies being done with RAN looking at word reading in connected text? Because I think that's a different process.
Yes.
Similar,
Yeah.
obviously, but I think that's a different step. Is that being considered much at all?
In the MRI stuff, less. In the behavioral studies, definitely.
Okay.
Yeah.
I'd be curious to see where that.
It's kind of the nature of like laying down in the MRI. It's a little bit trickier to get people to exactly. It's kind of a drawback. And I left lots of time at questions at the end, and I will make sure not to run into it. Okay. Last big section here. I want to talk about intervention. Well, before I do that, thank you. That was a good summary. Also, use RAN as a screener. It is such an easy thing and a powerful thing to use as a screener. Okay, last thing that I hope you all will find interesting. We have some studies about how high-quality reading, instruction, and intervention changes the brain. And it does multiple things. So, another meta-analysis. You can see that I love them. This one is several years old now, but reading intervention pre-post MRI studies, there are not a lot of them because they're hard to do. You have to get kids to come in for an MRI, do a whole intervention, and do another MRI, and not move during either of those MRIs. Both move in the scanner or move away. It's hard to find the right balance between curriculum developers that want people to study their curricula and researchers who want to be objective and not feel pressure to have a certain result. I have curriculum developers all the time, who want to sell, this box of reading instruction X, who say, "Can you do a pre-post MRI study?" And I'm like, no, I don't want to be beholden to anybody. I don't want to have any conflict of interest. And these studies are really hard to do, and they don't realize how expensive they are. MRI costs $500+ an hour to do. This is very hard. So there are not many pre-post MRI studies, but there are a few. So in this study, they ended up finding 8 studies to include in their meta-analysis that had enough data to be able to be compared. And when they looked at what parts of the brain were more active after reading instruction, now we're looking again at kind of a slice across the brain. So eyes would be up here, ears on each side, back of the head. So we're seeing again our friend the left inferior frontal gyrus. Also back here in, I guess you could call it occipital temporal. And then we've got this region up here in the middle of the brain, which is called the thalamus. And that is like a relay station. It's like taking information from one sensory modality and sending it to the other and things like that. So that kind of makes sense that we would see that. Another thing that we see, though, is this big chunk up in the right frontal section. And lots of studies have found that from intervention, you get kind of often a shift toward a more quote-unquote typical looking brain, but this part on the right frontal often comes up as an area that seems to be sort of like a compensatory strategy. Like you're going to kind of need to bring in like extra resources to be able to read well. And then you get this other little region here in the posterior cingulate, which is probably executive function related, best guess. But these are the things that kind of change on average as you get better at reading. I'm going to talk about a couple of specific studies that looked at other things. So this first study looked at functional connectivity, meaning parts of the brain that are active at the same time, meaning they're sort of working together. And so in this study, they had kids from 8 to 14 years, and a proportion of them had reading problems. Some were typical readers, but they followed everybody over 2 years. And they looked at which parts of the brain were active together during a word reading task and a phonemic awareness task. So they had to read 2 words and decide if they rhyme. Okay, so what we saw is that they looked at these different regions again. They've got a kind of a bigger temporal parietal region. But what they saw is that over time, good readers showed an increasing connection here between the visual word form area, which is really important for sort of orthography and sight words, up to the temporal parietal area, which is sound to letter correspondence and phonemic processing. So this got stronger in the good readers, and most poor readers didn't even kind of establish any kind of connection between those regions. So this makes sense. If you're not linking up sort of your orthographic processing with your phonological processing, you're going to have more trouble learning to read. Oh, look, I made it flash for you. Then the other thing is that with increasing reading skill, good readers then linked up these two parts kind of down in the visual part of the brain. And this idea is that they're switching from sort of a decoding strategy to a primarily orthographic strategy, right? Most of us don't decode most of the words that we read. We're seeing big chunks or whole words. And interestingly, the poor readers decreased rather than increased this connectivity. So the authors say that these results together suggest that superior reading ability is initially supported by phonological decoding with a decreased reliance on this strategy as reading becomes more automated. Kind of duh, right? Like, yes, this makes sense. You got to start with some decoding. But as you build that foundation of decoding, that lets you then make this kind of shift to a more efficient, sort of using more visual processing model of reading. So then we can look not just at which areas are functionally connected, but structurally connected. So I showed you these tracts back in the beginning, looking at the different arcuate fasciculus and another one that runs on the length of the bottom of the brain. And then also you've probably all heard of the corpus callosum, which is the tract that connects our two hemispheres. So this study looked at those tracts, and they looked at which regions became better connected as kids learned to read. Better. So this was an intervention study. They had 24 dyslexic kids who were about 9 years old, and they did 4 MRIs. So these folks were really ambitious. And they, over the course of this intervention, kids got 160 hours of a well-evidenced, multisensory structured phonological and orthographic intervention. And we're going to look at these white matter highways again compared to a control group who didn't get any intervention. So what we're looking at here, what I like here is that they're showing us individual kids and not the group means. So now we're looking at a different measure like fractional anisotropy, where less is better. And we are looking at the 2 different tracts in green and blue, and each of the kids are up there on the top, but we've kind of zoomed in on 4 kids here. So time 1, before they started intervention, during intervention, and after intervention. And what you can see is that the general pattern is that this is decreasing over time, which is what we want. This means that the tracts are getting better organized. But everybody's doing it in a little bit of their own way. This is not just a straight linear line for everybody. If we look here at their reading ability versus this measure that we just looked at before, you can see that there's kind of this inverse relation, which is what we expect, because more MD is bad. So this kid started out a pretty low reader with pretty high MD, and then as their MD decreased, their reading ability increased. So this is really good evidence that there's a direct relationship here, that this change is leading and causing differences in reading ability. And if we kind of zoom out, another way to look at this, again, same study, same tracts, but over the length of the tracts, we see kind of the same thing. And what's really nice here is that we see that these effects are only in the intervention group. The kids who didn't get any intervention and just got scanned a bunch of times, we don't see these changes. So that's why we need a control group. You can see that we have increases in FA, which is the measure we talked about before, which is good. I think I made a little note. No, maybe not. But in all the cases, kids are getting significantly better at reading in the intervention group, and they are changing their brain in a related way, and the kids who are in the control group didn't have any change and didn't get better at reading. So this tells us that intensive multisensory instruction strengthens these reading network connections that are so key to the reading brain. This guy right here, primarily the arcuate fasciculus. Oh, I did zoom in on this and explain it in more detail, but we just walked through it before. Okay, so we'll skip ahead so we've got lots of time for questions. Sometimes I forget what good PowerPoint animations I made for you. Interestingly, when we look at the different reading measures that they gave in this study, we've got the Woodcock-Johnson basic reading composite, and then the Tower Index, and then the Woodcock-Johnson reading fluency. Which column has the most bold numbers, meaning they're significant? Tower. And Tower, as you probably know, is speeded, single real word, and non-word reading. And so it's interestingly that these white matter properties that are changing, these are kind of things that are linking up different regions that let the brain be more efficient primarily. And so it's neat that it relates primarily to this speeded measure that requires more and more automaticity. And the kids were 9, so it makes sense that, that we're seeing that. But interestingly that this was pretty strongly related primarily to the Tower. So to summarize this study, this intensive reading instruction changes these important tracks, perhaps reflecting this multisensory approach that we're linking up all of these different parts of the brain. And we also did see some tracks that were less related to reading that showed changes, but only changes in the reading intervention group. So quality intervention changes local function, but also strengthens these connections. But honestly, I don't care what your brain changes as long as you get better at reading. Like your brain can turn purple and, have gold-plated edges and whatever, but it doesn't matter if it doesn't help you be a better reader in the classroom and get more out of instruction. All right, so to wrap up, what to do on Monday. I know it's only Thursday. Thought I'd give you an extra day. You all are extremely well positioned, and I think you're already doing this, but I want to say yay and thank you to continue to advocate for the key tenets of the science of reading. Every child needs relevant meaning on the things that they have difficulties in. We're not going to make them jump on trampolines. We're going to address their profiles of strengths and vulnerabilities, and using high quality instruction. Use a multi-component assessment battery in kindergarten, including RAN. This is so easy. And intervene early. I think what we're lacking brain data in, but the behavioral data is very clear that we cannot keep waiting for kids to fail. We can't say they're just a boy, they just have ADHD, they just have a family history. We'll watch and wait. We need to intervene early while the brain is still plastic and moldable, and kids don't start falling further and further behind their peers and feeling worse and worse about reading and about themselves as learners. If we want to build fluent comprehension, what the research tells us is that we, again, need to tailor to a child's profile of strengths and needs, so that you need to give them instruction in what's relevant to them. If they have great phonemic awareness, put your intervention time into something else. We need to build foundational accuracy via systematic, explicit, and multisensory phonics. And then, once that is in place, build automaticity and connectivity among these different parts of the reading network by authentic practice and general reading instruction that is engaging all of these parts of the network together. And one of the things I get asked about a lot is about repeated reading, because it seems like that is the buzzword to develop automaticity. But I did a deep dive, not on my research, but on existing research, and the really high quality studies on repeated reading show that it is not any better than the same dosage of not repeated reading. And I have a paper under review in the Reading League Journal about this that I hope will be out soon. If you are concerned about a child's reading, the intuition of an experienced teacher is one of the best indicators we have. So before we even ever put like a neuropsych type measure in front of a kid, an experienced teacher's intuition is almost as good an indicator. So trust your gut. Do not wait. Get them a comprehensive eval. And a lot of the work that I'm doing that I'm interested in right now is looking at the co-occurrence of mental health challenges in kids with reading. It seems like biologically there is a sort of propensity if you have either a mental health or a reading or language challenge to have the other. Essentially, you have a little bit of more vulnerability if you have one. And you might see in kids in your classrooms, often you don't have one diagnosis, you have more than one diagnosis. And so reading problems are so oftenly co-occurring with mental health challenges, I think it's time to start assessing mental health at the same time we assess kids for reading difficulties. And on that hopefully positive and supporting all of our learners note, I will say thanks for all of your attention this afternoon and glad to have lots of time for questions. I think we have a mic for questions so that for the recording we can make sure that everyone can hear them.
Oh, thanks. Do you think these changes in brain architecture actually remain permanent, or do you think they atrophy after the intervention is removed?
Good question. I don't think we have any actual data to speak to this. I would imagine that it kind of relates to the degree to which the child can build on this intervention as a platform to kind of continue that level of ability. I think if you had a sort of a slide back, a summer slide type loss of skill, you would probably see a reversal of these. But at the same time, we really don't have good evidence. So it's a good question. I know you have questions, y'all. Here's the mic, just a sec.
Is what we're seeing in kids relatable to adults or college students in terms of interventions, or are we not seeing that population coming forward to say, hey, I can't read?
Good question. And that's the population that I started working with, was high school students. And so I think we would see a lot of these same kinds of things. I think often the students who are still struggling at high school age or college, in some ways may be fundamentally kind of a more severe reading difficulty than the one that may have been able to be remediated earlier, but not necessarily. Lots of kids are clever and skate by and get missed and really kind of work the system and end up getting to high school or college or adulthood without ever being identified. And so you have a lot more life experience, which has impacted the brain in different ways over that time. So there may be some differences. But because we all have to kind of build a reading brain, it's not the same thing for language, where from birth we are all kind of set up to learn language in a certain way. There aren't many studies. And again, because it's harder to get groups of folks like that together to do the research, and it's kind of like sparkly and new to say we're going to treat this early and it gets more research funds. But I would imagine you would see generally the same similarities because they're kind of building up these reading connections in the same way that a younger kid would. And in studies, which I didn't really talk about today, when we compare groups of more like middle school age kids with dyslexia versus typical readers, there was a thought for a long time that maybe the dyslexics were just immature and they looked like younger kids of the same ability, but they actually don't. So they look kind of qualitatively different than, say, first graders who are at the same reading level as these fourth graders who are poor readers. So it's a little bit of a contradiction what I just said, they're qualitatively different, but also we would probably see similarities. So I don't know, and another thing we were talking about with some of the cell folks today is what makes some kids more easily able to sort of benefit from intervention and other kids get high quality intervention and seem to still struggle despite us kind of giving it our best efforts. And it's a question I'm really interested in. And I want to look at kind of these kids, and I hate the term treatment resistors because they're definitely not trying to resist the treatment. They're just not, it's not working for them. So I'm very curious to look at that, and there's not very much out there on it. Did I talk enough words to finally answer your question? I agree. I think it's worth trying. And it's definitely it's for sure worth trying. We shouldn't just say, their brains are old, they won't, benefit from this. But there's also such a lack of age-appropriate materials that are, relevant for them and things like that. Even by like fourth grade, the types of materials out there are pretty limited. So I think that's a barrier that we could probably address and benefit folks.
Are there meta-analysis on the multilingual learner, the length of time it might take a student who's learning a second language to develop well in the second language?
This is a really good question. I don't know of any meta-analyses per se. There's actually one of the first studies that I did in the world of reading when I was an undergrad. We were looking at kids who are Spanish-English dual language learners who either learned reading in each language sequentially, so learned English or Spanish first, or learned both in like a 50-50 immersion school. And there were effects on kind of what your reading strategy was based on the language that you learned in first. So if you learned in Spanish first, where there's a much more predictable sound-to-letter correspondence, you tended, when you then learned English, to rely on that strategy a little bit more. You often had better phonics and decoding because you were really well practiced in that, but it was harder to get used to this system where we have less regularity in English, and vice versa. So you kind of brought the English characteristics to Spanish. So I don't know about length of time. There are several researchers who do really good bilingual assessment and intervention work who I could point you to, but I don't know a ton about exactly that topic, other than that you're kind of bringing the characteristics of your home language. But then we also know that on average, kids who are dual language learners may be coming from less advantaged households, different language kind of quality backgrounds, things like that, again, on average. And so it's hard to tease apart what is being bilingual versus what is potentially like going up with systematic racism because you are a person of color growing up in the US, or things like that, or having a family that is nervous to speak to you in English because they, don't want you, or nervous to speak to you in Spanish because they want you to learn English, or all of these other kind of things that get tied up with it. But I'm glad to point you to some folks' work on that could probably answer the question better than me. Yeah.
So you talked about RAN and how predictive it is and correlative it is. Is there any benefit to helping kids actually practice that skill, and what would that look like?
Thank you for asking that question. We talked about this earlier today. So I should have brought this up because it seems like a great idea. Interestingly, what we think RAN is reflecting is sort of the brain's capacity to automatize for reading and languagey things. And this is not something that we have any evidence that we can change. So similar to working memory or nonverbal IQ, this is something we think of as kind of a set characteristic across people, and some brains are set up in a way that they can build this automaticity quite easily, and others not so much. And so there have been studies that have had kids do this over and over. They get very slightly faster at it, but it doesn't improve their reading. So it is much better to understand it as a screening metric and use it that way. And if a kid has weaknesses in RAN, important to keep in mind that they may initially look accurate, so they may kind of meet benchmarks in kindergarten, first grade, maybe even early second grade, but when the demands are shifting more to efficiency and fluency in connected text, they're likely to have more and more difficulty. So it's a good screening measure because nothing else in screening really kind of captures it. And we really just need to watch it and sort of start intervening on all of the other things around it. So strengthening spoken language and language comprehension, and all of the phonics and phonemic awareness and orthographic knowledge and everything else that goes around with it, essentially to try to work around the challenge that it presents. I wish. If I had a magic wand, it would be like, we could fix your RAN.
It's so funny that you asked that question because I just Googled, can you teach RAN? And if somebody tells you to do that, it says run.
Yes.
And it's Wolf study on here. But my question is, everyone tells us, oh, you have to have really good intervention to intervene with these kids. Where do you research to find out where there's quality intervention instead of just somebody selling you something that they say is good?
Excellent question. There is a website that used to be better curated, it's still somewhat helpful, called the What Works Clearinghouse from the Institute of Education Sciences, which is kind of like the NIH, which does health, of education. They review studies, and for each of the studies, they determine if the study was of good enough quality. So for example, like, did half of the kids drop out of the study, or things like that. So they say, is the study pretty good quality or not, and did it make change in different areas, so like vocabulary, sight word reading, reading fluency, comprehension. I say it's a pretty good site because I don't always agree with their metrics for study quality. So, for example, some very widely used interventions take the approach of we're going to put all of these first graders in this particular widely used program, and we're going to use that program, and halfway through the year, we're going to see if they're making progress. And if they're not making progress, we'll take them out of the study, and we'll leave the kids making progress in the study. And then at the end of the year, they say, look, the kids got better. And so that counts as positive evidence in a good study. But we can all kind of recognize that if you just take everybody out of your study who wasn't responding, it will look like your intervention works. So that's a good place. I know like accessing the scientific literature is a huge barrier. You get paywalls, you get things like that, but looking up to see if there are studies done by like researchers at universities, not, like the Elizabeth Norton Reading Program Institute or something, if I'm trying to sell you the Elizabeth Norton Reading Program, looking at if there is data out there. And then most of the curricula that are trying to sell themselves to you will have information if they have done these studies. And then I think you have to be a careful consumer and try to look at that and see who did it and how many kids was it done on and those kinds of things. But I realize that is easier said than done because teachers don't get training in how to evaluate study quality and things like that. So I think it's do the best you can and work with partners in your school, leaders, call the folks at CEL, I'm going to say, put you on the spot, and look for that kind of unbiased and also like study quality things like random group assignment. And you can't do a double-blind reading intervention study until we have robots that can teach reading. But you can have these things that make studies higher quality, like random assignment and large samples and so on. But it's no. No, maybe later if you have certain ones in mind, I can tell you what I think, but this is being recorded, and so we'll do that afterward.
I'm curious if when you were doing like the brain scans and thinking about children, if like you took like any trauma into consideration, or if any of those metrics were taken, and if they impacted the brain and how they read as well.
This is a good question. I don't know of any studies that have looked at that directly, because it can be in so many different ways, right? You can have trauma about so many different things, including being a poor reader. I think this work we're starting to do, trying to look at sort of stress and mental health and things around it, trauma is a good thing to look at. We know that chronic stress and kind of the effects of trauma affecting the stress system and sort of stress reactivity and things like that. Essentially, what we're learning is that living in an environment like that makes your brain speed up its growth, because your brain is like, this environment is really difficult. I want to kind of get grown up as fast as I can, because when I'm little, I'm more susceptible to the effects of stress. And so it may be that kids who are facing chronic stress, trauma, and things like that they may be these kids who have more, we see less benefit from intervention because their brains are kind of trying to be like less flexible early on. That's very speculative, because I don't think there are any studies that have actually linked the reading with the trauma, but we know from sort of the chronic stress literature that your brain is sort of making itself less ready to learn new stuff, but to be more mature faster. It's a good question.
So I'm seeing more and more publishers of screening assessments incorporate RAN as one of their protocols, but a lot of schools in Indiana use, like, let's say, a curriculum-based measure for early reading skills in kindergarten and a separate RAN measure. So I was in this district where we had 20 kindergarten classrooms and we're doing these data team meetings. Talk to me about how you might help a data team explore RAN in relation to their other skills, right? So you get like a risk score. We know the student is at risk. It's pretty easy if RAN is low also, like, yikes, okay, intervene quick and fast and intense. But what about if RAN is high and other reading skills are low, or vice versa?
Great question. It's still hard, even when you give the best screening battery, to know where to draw that line. I think it's one of the biggest questions in the field. And it's always going to be a trade-off of, do you want to identify more kids to get them intervention, or fewer kids because you have not as many resources? Who do you give services to? I think difficulties in one or the other, sort of anything else, but say phonemic awareness or RAN, you still jump in right away. I think the difference is it's easier to know what to do with a kid who has low phonemic awareness, right? We know how to fix that, but to the earlier question, with RAN, it's much trickier. I think you want to look at the rest of the profile, and if there are other areas that are, say, like low average, like that alone wouldn't have been a concern. But if, say, sort of language comprehension or letter knowledge is a little on the low side, those things together with RAN are going to make that kid more likely to struggle. So I think for the kids with low RAN, everything else technically in the typical range, I would try, and I know this is easier said than done, and resources are, not infinite, to support all of those other levels in that kid, because likely that is the kid at the end of second grade benchmarking who we were like, where did they come from, like falling off the edge when you start getting to these higher reading sort of demands. So I think any one other than letter name or sound knowledge, because we know that we can just, for almost everybody, teach you that and then you get to the typical range. Either one is worth intervening on, but it's a hard question of how low is low of RAN do you need to worry about, and we don't have good evidence on exactly that. But to your point, it is a good practice to use a published, standardized, normed RAN measure, because then at least you know where this kiddo stands kind of in relation to their age or grade, as opposed to creating your own, which is better than nothing, and at least comparing them to other kids in the classroom. But even if it's not the same part of the kind of bundle that you have, I think it can really still add important information.
Last call for questions.
All right, thanks so much for your attention. My info is up here. Oh, only half of my lab people showed up. That's funny. Oh, look, there's the rest of them. Thanks to all of you for your attention. Thanks again to Sel for having me, and hope you have a great rest of your day.
So we are going to share this PowerPoint with you. I saw some of you feverishly trying to take pictures of the slides. So you'll get the slide deck. There'll also be an evaluation that comes out afterwards. If you give us a bit of feedback, we'd greatly appreciate it. And we have a lot of food left over. It will go to waste if you don't take it. So make a stop at the food table on your way out. Thank you for coming.